Hello and welcome to our exploration of network and graph theory. In our previous video, we laid a foundation by discussing the fundamental language of network. Today, we are diving deeper into the world of interconnectedness, focusing on network connections and topology. Today's goal is to gain a comprehensive understanding of network connections, which are the core of any network. These connections will be quantified using a crucial concept known as degree, a metric that plays a pivotal role in counting the number of edges connected to each node. Then we will explore hubs and move to investigate degree distribution, a key concept that reveals the distribution of node degrees within a network. Last but certainly not least, we will tackle the conceptual distinction between distributed and the centralized network. This exploration will be pivotal in illuminating the diverse approaches to the network architecture. Let's start today's session with network connections. Connections lie at the heart of network. They serve as the foundation and backbone of any network, playing a crucial role. Connection essentially represents the link between different nodes or entities within the network. Connections are akin to the vital threads that stitch together the fabric of any network. They play an indispensable role in fostering communication and interaction between these nodes, thereby facilitating the smooth and efficient flow of information throughout the network. Networks, whether they be social, transportation, or computer network, rely heavily on the nature and abundance of connections. These connections dictate not only the speed and efficiency of data transmission but also the resilience of the entire network. A network with robust and diverse connection is better equipped to withstand disruption and continue functioning seamlessly. Furthermore, connections in network are not uniform. They come in various types and strengths. They find real-world application in modeling a wide spectrum of complex systems. These include, but are not limited to, social networks, where connections represents interpersonal relationships; transportation network, where connections mirror the route and routes that enable the movement of people and goods; the computer network, where connections define the pathway for data transmission and communication. These tangible examples emphasize the practical significance of understanding and harnessing the power of network connection in our modern interconnected world. Now the question arises, how can we precisely quantify a node connections within a network? What truly defines the scope of a node connectivity? Well, this crucial parameter is referred to as degree of connectivity. Node degree stands as a measure for gauging how intricately a node is woven into the fabric of a network. In simple terms, node degree is a way to measure how connected a node is in a network. The node degree of a node can be calculated by counting the number of edges that are connected to the node. The higher the node degree, the more important the node is in the network. Node degree is not just a theoretical concept but a practical tool. It helps us identify the most common nodes in a network, understand how information flows through the network, and even predict how the network might behave in future. In other words, node degree helps us explore and understand networks better, revealing their hidden structure with clarity and accuracy. Now imagine a network with hundreds or even thousands of nodes. Visualizing and manually counting network connection for each node become impractical and time consuming. That's where adjacency metrics come to the rescue. The adjacency matrix, which we have seen in the earlier video, is a representation of a metric of a network in a matrix form, where rows and columns in the matrix represents the nodes and the number in each cell indicate whether there is a connection between the corresponding nodes. Here, an example of the adjacency matrix of our previous network. In this case, a value of 1 means there is a connection, while 0 indicates there is no connection between the nodes. Now let's dwell deeper into the utility of adjacency metrics by exploring their role in calculating node degree. To calculate node degree, we simply sum the values within a respective row or column. Node 1 has only one connections with node 5, so we sum up the values in this row, which gives us 1. Similarly, we calculate the degree for nodes 2, 3, 4 and 5, which are 1, 3, 1 and 2 respectively. What's intriguing is that an indirected network, the adjacency matrix assumes a symmetric structure. This symmetry ensures that both the row sum and the column sum yield the same node degree. This mathematical tool proves especially efficient when dealing with larger network, where the visual assessment of network connections become unfeasible. Let's move our focus to the directed network. But before we define degree of connectivity in a directed network, it is essential to solidify our understanding of what a directed network entails. In a directed network, the connections between nodes exhibit a specific directionality. This signifies that the relationship between nodes are inherently symmetric, a notable departure from the symmetry found in the undirected network. Since a directed network has two types of connections, incoming connections and outgoing connections, consequently, each node in a directed network possesses not one but two distinct degrees, the in degree and the out degree. To clarify further, the in degree of a node corresponds to the number of incoming connection it receives, while the out degree signifies the tally of outgoing connection it initiates. To calculate the in degree and out degree of a node using the adjacency matrix, we need to understand how matrix represents the connection between nodes. Let's take a look at an example adjacency matrix for a directed network. In this matrix, the row represents the source node while the column depicts the target node. When there exists a connection from source node to target node, the corresponding matrix entry assumes a non-zero value. Let's start by determining the out degree of a node. To achieve this, we simply count the non-zero entries within the row that corresponds to our chosen node. For instance, if we aim to ascertain the out degree of node 1, we focus on the first row and tally the non-zero entries. Let's calculate the out degree of node 1 together. Look at the first row. We see there is only one non-zero entry. Hence, the out degree of node 1 is 1. Now shifting our attention to calculation of in degree, we must count the non-zero entries within the column corresponding to the target node. For example, let's determine the in degree of node 2. We look at the second column and count the number of non-zero entries. Let's do the calculation together. Looking at the second column, we see that there are two non-zero entries. Therefore, the in degree of node 2 is 2. Additionally, we can introduce the concept of total degree, defined as the sum of in degree and out degree of a node. As I stated earlier, network connection is one of the measures to assess the significance of a node in a network. Given a network, we can define the importance of node in terms of connections, which is called the degree hub. In simple terms, a hub is a node in a graph that has high number of connections compared to the other nodes. It acts as a central point connecting various parts of the network together. As you can see here, the node marked as hub has a magnitude of connections radiating from it and or converging to it, connecting different parts of the network together. This hub is like the core of the network, connecting various devices and making sure that they communicate with each other smoothly. It's like the heart of the network, making sure data flows uninterrupted and network performs at its best. These connections in a network can represent different types of relationships like social connections, transportation routes, or web links. In transportation networks, Hubs are important places like airports or train stations that connect different routes and make travel efficient. Similarly, on social media platforms like Facebook and Twitter, hubs play a crucial role in connecting users and enabling quick interactions. These hubs function as a catalyst, rapidly disseminating information across their vast network with remarkable efficiency. In a graph, a node degree tells us how many edges are connected to that node. Degree distribution is a way to understand how common different degrees are in a network. Degree distribution is simply referred to a probability distribution that informs us about the prevalence of nodes having specific degree. In other words, it explains how many nodes have a particular degree. By analyzing the degree distribution, we can gain a deeper understanding of how nodes are connected and how information flow within the network. It is a way to analyze the frequency of different degrees within a graph. Let's move on to a practical example. Picture a simple graph with nodes labeled from 0 to 9. The lines connecting these nodes represents edges. To construct a degree distribution, our initial task is to compute the degree of each node, documenting all the degrees of the nodes within the network. Now that we have calculated the degrees of all the nodes, we can move on to creating the degree distribution. In simple terms, after we figure out how many connections each node has, we can create a chart that shows the distribution of these connections. To do this, we need to count the number of nodes with each degree value. Let's start by counting the number of nodes with degree 1. In the network, there is no node with degree 1. Now let's count the number of nodes with a degree 2. There are two nodes with degree 2, node number 8 and 9. Similarly, we count the number of nodes with degree 3 and so on. Degree distribution is then represented using a histogram or a bar chart. On the x-axis, we have the degree values, and on the y-axis, we have the frequency or the number of nodes with that degree. Degree distribution can manifest in various configurations, ranging from a bell curve to a power law distribution or even a uniform distribution. Each distribution tells us something unique about the network. Now you might be wondering, why is degree distribution significant? It is important because it helps us understand how strong, efficient, and vulnerable the network is. For instance, in a social network characterized by power law degree distribution, we frequently encounter a select few nodes known as hubs that exhibit substantial connectivity. These hubs wield substantial influence over information dissemination and can significantly impact the network overall performance. Conversely, a network featuring a bell curve degree distribution denotes a more balanced and uniformly distributed interconnectivity. Such networks often exhibit greater resilience in the face of random failure but may experience slower information propagation. Degree distribution has practical application in various fields. It helps us understand the spread of disease, analyze social media influence, optimize transportation network, and even study the structure of the network. So, the next time you come across a graph or a network, pay attention to its degree distribution. It holds valuable information about the network behavior, resilience, and efficiency. In our previous section, we examined the overall degree of connectivity in the network. But now we are going to shift our focus to another crucial aspect that defines a network: how centralized or distributed they are. Centralized and distributed network are two contrasting architectures that refer to the organization and structure of how components, data, and control are managed within a network. Let's start by understanding what a centralized network is. In a centralized network, all components, data, and decision-making authority are concentrated in a single central node or entity. This central node serves as the epicenter for communication, control, and information exchange. Think of it as the heart of the network where all important decisions are made. Centralized network offers some distinct advantages. They are often more efficient in terms of resource allocation and management since the decision making can be made quickly by the central authority. Additionally, troubleshooting and maintenance are relatively straightforward as there is a single point of control. They have a hierarchical structure with central control. However, there are some downsides. Centralized networks are vulnerable to a single point of failure. If the central node goes down, the entire network can become inaccessible. Moreover, scalability can be an issue as the network grows larger, as the central node may become a bottleneck for data and communication. Centralized networks are often seen in organizations where a clear hierarchy and authority structure are essential, such as a traditional corporate environment. Now let's shift our focus to distributed network. In a distributed network, component, data and decision-making authority are spread across multiple nodes or entities. This type of architecture promotes decentralization and collaboration among nodes. Distributed networks have their own set of advantages. They tend to be more resilient to failures since the network can continue functioning even if some nodes goes offline. Scalability is often improved as new nodes can be added without significantly affecting the network performance. However, managing a distributed network can be more complex. Decision making might be slower due to the need for consensus among nodes. Moreover, ensuring consistent data across all nodes can be challenging. Distributed networks are prevalent in scenarios where resilience, collaboration, and peer-to-peer communication are crucial, like in peer-to-peer file sharing systems or blockchain network. An example would be internet, where there is no central control and information can flow through multiple routes. In many real-world scenarios, we find hybrid network that combines elements of both centralized and distributed architecture. This allows for a balance between efficiency and resilience. For example, a hybrid network may have a centralized control structure and a distributed data storage.